So in this clip, we look at the example of an operator on F2 that takes WZ to minus ZW. So in the case when F is the reals, this is clockwise rotation by pi over 2. And a rotated vector is not a scalar multiple of itself. And so maybe just for emphasis, I'll say a real scalar multiple of itself. So there are no eigenvalues. Right, so if we have some vector and it's rotated clockwise by 90 degrees, it's not going to end up parallel to how it started, right? Okay, so then the only invariant subspaces are 0 and R2. On the other hand, if we take F to be the complex field, then let's see. So if WZ gets mapped to minus ZW, and this is supposed to be a scalar times the original thing, then comparing the first coordinates gives us the equation minus Z equals lambda W, and comparing the second coordinates gives us the equation W equals lambda Z. And so if we put this one W equals lambda Z in for W right here, then we have this one. And so adding the adding the Z to both sides, we get lambda squared plus 1 Z equals 0. And so this implies that Z is equal to 0, or lambda is equal to plus or minus I. However, if Z were equal to 0, then W is also going to be equal to 0. And then that would mean that we started with the 0 vector and we wouldn't get an eigenvector, so we can cross that one off. The corresponding eigenvector is IWW for lambda equal to I, and minus IWW for minus I. And you can check on your own that if you apply t to either of these vectors v, then it's the same thing as multiplying it by I or minus I, respectively.